Welcome to Thought Leaders, brought to you by Space Center Houston. I am Steve LeBlanc, an engineer by training and the Vice President for Business Operations and Facilities at UTMB Health, proud sponsor of the Thought Leaders Lecture Series. Tonight, we are exploring nuclear technologies in space as a way to provide energy for long-duration missions to the moon and beyond. As a major medical provider, UTMB knows about the importance of reliable energy supplies. Our facilities team manages critical primary and backup power and utilities for 4 campuses, a network of hospitals and clinics, our 5 schools, and a vibrant research enterprise. Most of us have experienced the challenges of losing power, whether due to storms, high demand, or freak accident. It's usually little more than a short-term inconvenience, or it can be, as in the case of patient care, a matter of life and death. Now imagine a scenario where you can't make a call, fire up a backup generator, or wait for the service trucks to roll through your neighborhood, where parts are at least 240,000 miles and a 3-day spaceflight away. Tonight's lecture explores how NASA intends to establish energy sources on the moon, circumventing the potential nightmare of loss of power in space. We'll be hearing from 2 experts in the field, Harlan Bowers, President of X Energy, and Peter McGrath, Vice President of Business Development for Intuitive Machines. These companies are partnering with Maxar and Boeing to develop preliminary designs for the Fission Surface Power Project, a joint initiative of NASA and the Idaho National Laboratory, with a goal of creating Lunar Nuclear Power Systems. Providing reliable power is just one of the challenges of long-term human existence on the moon or in deep space. Fortunately, bright minds are hard at work at NASA and with companies such as X Energy and Intuitive Machines to turn science fiction into reality. I look forward to a fascinating discussion and thank you for joining us for another Thought Leaders Lecture.
Hello, I'm William T. Harris, President and CEO of Space Center Houston, a dynamic science and space exploration learning destination and nonprofit science center. We also have the privilege of serving as the official visitor center for NASA Johnson Space Center. We share the story of human space exploration, past, present, and future, with more than 1.25 million visitors annually from around the world. Thank you for joining Space Center Houston's Thought Leaders program, Lunar Nuclear Power Systems, presented by University of Texas Medical Branch. Our Thought Leader series brings you space and science experts from across the country who provide insights and perspectives on space exploration. Space Center Houston offers robust learning experiences that enable you to be a part of NASA's mission. In addition to our extensive collections, you can experience new exhibits and live programming, so there's always something new. Now on to our program. Power generates everything here on Earth, from our handheld devices to providing food and water. As humanity expands its presence in space, we'll need a sustainable source of energy too. We know that solar power is limited in space, so what's the alternative? Portable nuclear energy can be used to sustain lunar habitats and rovers, but it's not without its set of challenges. In our discussion today, we'll learn about nuclear energy and how it can power exploration on the moon and beyond. I'm delighted to welcome our panelists for our August Thought Leaders series. Our first speaker is Peter McGrath. Peter has over 33 years of aerospace project and program development, capture, management, and business development experience. With a bachelor's and master's degrees in aerospace engineering and a master's of business administration, Peter has spent his career leading and supporting NASA, Army, Air Force, international, and commercial programs. Peter currently serves as the Vice President of Business Development for Intuitive Machines and is responsible for expanding future business opportunities and growing the business. Founded 9 years ago, Intuitive Machines has been awarded 3 NASA Commercial Lunar Payload Services contracts to deliver payloads to the lunar surface and a Phase 1 contract for Department of Energy and NASA's Fission Surface Power Systems. We're so excited to hear his remarks today. Our next presenter is Harlan Bowers, who leads X Energy's development of the XE Mobile, a state-of-the-art transportable nuclear power source, as well as government opportunity business development and various corporate initiatives. At X Energy, he has overseen business strategy analysis, design development, regulatory assessment, and Nuclear Regulatory Commission engagement, as well as strategic partnerships. Harlan has also led X Energy's efforts to capture multiple government contracts, including a nuclear thermal propulsion concept development with NASA. He holds a bachelor's in aerospace and ocean engineering from Virginia Tech and a master's from the University of Maryland, College Park. Welcome to you both. I'm very excited to hear your remarks, and I'm excited about our conversation today. First, we'll hear from Peter.
Thank you, William. And it's a pleasure to be here today to talk about fission surface power. And I want to start off by giving a little background of what fission surface power is. It is the current acquisition activity that is going on between the Department of Energy and NASA to look at how we're going to actually put reactors on the surface of the moon that can power large systems. Recently, DOE awarded contracts to 3 vendors, IX being one of them, but the other 2 are Lockheed Martin and Westinghouse. And in this phase 1 contract that we've been awarded, our focus is really about maturing the design to a point where we can actually help NASA define the requirements for a final competition that will decide who will actually build a reactor that will launch in 2028. So that's the purpose of the contract. So this contract was awarded to IX, which is a joint venture between X Energy and Intuitive Machines. So I represent Intuitive Machines today, but you're going to hear later from Harlan Bowers, who represents X Energy. Along with that team, we have 2 large teammates that are part of it. That is Maxar Technologies and Boeing. So now I want to talk a little bit more about what IM is. So Intuitive Machines, as was mentioned by William, we were founded in 2013, and we are a company really focused on lunar infrastructure. Currently, we have 3 contracts to land on the lunar surface. The first mission we're going to fly is in December of this year. The second mission we plan to fly is in June of next year, and the following mission would be in April of 2024. Each of these missions are going to land on the lunar South Pole and survive for anywhere from 10 to 14 days and provide critical science back to NASA. The first mission is going to Mare Crisium, which is a location in the equatorial region of the moon. The second one goes to the lunar South Pole and actually drills for water ice. And the third one actually has 5 rovers on it and lands in Reiner Gamma. We'll look at, there's a polar swirl, which is an electric anomaly on the pole that it will actually inspect. So a lot of great science that we're going to do in these 3 missions. But as part of this, IM actually built out more than just landers. We actually went out and put together a lunar data network, which is a bunch of dishes around the world that allow us to talk to systems in and around the moon. And we're also putting satellites in lunar orbit to allow us to do data relay services to those systems in orbit or on the surface of the moon. And we're also building one creative thing on our second mission where we're actually building a hopper, which is more like a lunar drone that will hop into craters or permanently shadowed areas on the moon and experience what is in them for the first time. So some really exciting things that we're doing as we create this new lunar infrastructure. So to give you a little background of where fission surface power comes from and the purpose behind it, I wanted to show a little bit of a look at what NASA's long-term vision is. As they talk about Artemis, they're looking at how do they expand and bring humans back to the surface of the moon and stay. And so when you look at doing that, they have a good incremental plan to get there, of which I mentioned CLPS, or Commercial Lunar Payload Services. That is one of the precursors to put humans on the surface because it allows us to evaluate and look at locations where humans are going to go and actually what tools and things they need to use to explore. The next thing they talk about is really Artemis 1, which actually is planned to fly here, I believe, later this month. And then it's an uncrewed flight of Orion that will go around the moon and validate both the Space Launch System and Orion. They have a second mission planned in about 2 years that will actually take crews around the moon. And then ultimately we will get to a point where humans will descend to the surface of the moon using human landing systems. We're also going to see them put what they call the Gateway, which is a small orbiting station around the moon that they'll use as a way station for these future human missions. So as part of this, we're getting to a point where humans will live and survive for about 7 days on the surface of the moon. That's the first lunar missions. But to really want to live or expand longer than 7 days, you need to have a continuous power source. And that's where fission surface power comes in. When you look at typical environments, a lot of times we use solar power, but you don't have the access to the sun all the time on the moon. Most days on the moon, when you look at equatorial times on the moon, it's about 14 Earth days that you have for a lunar day, and it's about 14 Earth days as the lunar night. When you look at the South Pole, it's even worse because it could be as many as 3 days for a lunar night or 3 months, depending on shadows. It's a lot like living in Alaska, with the exception that the sun kind of bounces across that area instead of actually disappearing for long periods of time. And when you look at the temperature changes, it goes from about 273 degrees Fahrenheit during the day to minus 307 degrees Fahrenheit during the night. And so you need a system that can survive those things and provide continuous power. And that's why NASA asked industry to look at what they could do with fission surface power. So what I'm showing here is basically our concept on the left, which is basically a large structure that can provide what NASA asked for was 40 kilowatts of power out of the reactor 1 kilometer away, because they want to have it far enough away that the radiation effects don't affect the astronauts. And the way the reactor basically works is you have a power source, which is a nuclear reactor, which Harlan will talk more about in a minute, and it generates heat. And that heat comes up and it drives these pistons that as they cycle, they generate electricity. It's about 30 to 40% efficiency. So 30 to 40% of that thermal heat coming off the reactor is converted into 40 kilowatts of electricity. The rest of it has to irradiate out, and it goes up through these radiators and irradiates out into space. And so that's what basically this fission surface reactor is, or fission surface power is. And it's going to generate 40 kilowatts of power, which, to give you an idea, about a 2,000 square foot house uses about 1 kilowatt per hour. So it's significantly larger than what you would consume at a typical house. And the idea is that is going to provide power for habitats, for large human rovers, for even the ability to mine and refine water and oxygen and other resources on the moon. So with that, I'll hand it back to you, William.
Thank you, Peter. That was absolutely fascinating. I'm looking forward to our conversation a little bit later. And this really does revolutionize our ability to keep humans alive and well and productive on the surface of the moon and other bodies. So now we'll turn it over to Harlan before our conversation.
Very good, William. Thank you very much for the opportunity to talk about fission surface power as well as other things that we do. Let me start by a quick summary of who X-energy is. X-energy was started in 2009, not to explore space, but to make an impact on Earth by reducing the amount of use of fossil fuels by deploying nuclear power plants. We have 4 products that we're currently working on. One is a grid scale, 80 megawatt electric pebble bed modular high temperature gas cooled reactor. We refer to it as the XE100. And we received in 2020 a $2.4 billion cooperative agreement with the Department of Energy to complete the development of that system, build that system in southeastern Washington state, and commission and operate that system by the 2028 timeframe. So commercial reactors is our primary area of development. We've also been working on microreactors. There are many applications for remote communities, disaster relief activities, such as hurricane recovery, where a small transportable reactor would be of great value to return facilities like hospitals and water treatment plants back to operations shortly after some kind of disaster occurs. Third is these space nuclear applications, and there are a number of areas that NASA and other areas of the U.S. government are pursuing for application of nuclear on space systems. Fission surface power, which we're talking about today, is one of those systems. The other is nuclear thermal propulsion, and we can talk a little bit later, William, about the history of nuclear thermal propulsion and what can be accomplished with that. The fourth product that we develop and will deliver is nuclear fuel. And while there are several different designs for nuclear fuel, for our types of reactor, what we have chosen to use is a ceramic-coated uranium particle. It's referred to as tristructural isotropic particle fuel, or TRISO fuel. It was originally developed in the 1940s. The concept was created at Oak Ridge National Lab. There's been development of this type of fuel and these types of reactors in Germany, South Africa, Japan, and most recently China. And this is the basis of all of the systems, the reactor systems that X-energy is developing today. They all use this tristructural isotropic fuel in some manner. So let's talk a little bit about fission surface power and the subsystem that we refer to as the heat generation system. So the way, as Pete had described, the way these overall power generation systems work is you need a heat source. You transport that heat to a power conversion system. That power conversion system converts heat into electricity, and then the electricity is distributed, modified, converted, and delivered to either other parts of the space system or delivered to the user, in this case, at the end of a 1 kilometer cable to the astronauts and their habitats. So the way the reactor works, let's talk about that heat generation system. First is, this is a fission system that we're talking about, so it is uranium based. Uranium, and specifically we're looking at uranium-235. And we put those particles, those TRISO particles, in a sufficient quantity inside the reactor core such that the neutrons starts to generate more neutron releases, and that neutron release is called criticality. And so as criticality rises, the heat inside that core starts to rise as well. Now, how do we control the reactivity? We use something called a control drum, and the control drum has something called a reflector on that drum. And so we can absorb those neutrons, or we can reflect those neutrons back into the core to increase power or to decrease power. So as we create reactivity and we create more power, we create more heat. So we need to transport that heat, and we do that through a mechanism that we refer to here as the heat transport system. And in this particular case, it could be the use of a gas, a heated gas, and we flow that gas to the power conversion system, or it could be a set of heat pipes that move a liquid, a hot liquid, to the power conversion system where they cool and the liquid returns back down to the reactor. I'll pause here, and William, if you have any questions in regards to how the reactor works, we can start the conversation on that.
Great. Well, thank you so much for that explanation. That was a really complex scientific description that you simplified in a way that was really comprehensible. I think that was really fantastic. Just a quick question for you, Harlan, about the control component, control cylinder. What is that actually composed of that enables it to control the heat?
Yes, that's a great question. So the terrestrial commercial reactors and the space reactors would use the same materials, which is boron. So boron is a great neutron absorber. And so when we want the reactivity to increase, we rotate the boron, we call it a lens, we rotate the boron lens away from the reactor. When we want the reactivity to stop, we rotate that boronated lens into the reactor. It absorbs the neutrons, which kills the reaction.
Wow, absolutely fascinating. So I'm curious about how this idea came about to have actually fission surface power on the surface of the moon. And it is a very different environment. You don't have the same atmosphere as Earth. Are there factors being on the lunar surface that affect its efficiency or maybe enhance it compared to having a fission source here on Earth? That question could go to either of you.
Well, I mean, I'll start with the comment that, there's always a trade-off when we look at lunar systems or space systems about solar rays. I mean, quite often, most people attribute satellites have solar panels that collect power, and that actually is how you keep things alive. Because when you're in space, you go through periods of darkness where you're not seeing the sun, but you can use batteries to cover those periods of times. But as long as you're going around in a cycle in which you're not exposed to darkness for too long, the batteries don't have to be too big. Well, the problem you get into when you get to the surface of the moon is, and you're seeing this, by the way, with some of the payloads flying on the commercial lunar payload service contracts, there are actually payloads flying now that are going to survive the night, but they're about 70% of their mass is batteries. And the payloads are really small because you can't have that. You need a lot of stored power to stay through the night. So when you start looking at the problem and you say, hey, I want to generate something like 40 kilowatts, the batteries would be insurmountable. And so it kind of drives the architectural shift that says, hey, if I need to survive 3 months of darkness or even 14 days of darkness, I can do that much more effectively with a smaller reactor or a larger scale reactor like we're talking about. And that provides continuous power. So you don't have to worry about the ups and downs of having to store on a battery and then drain a battery and then store on a battery and drain, right? You don't get that much life cycle loss on the batteries. So I'll stop there and let Harlan talk more about the reactor side.
I wanted to add to that, and thank you, Peter, that there are other nuclear-based solutions that have been developed in the last 40 to 50 years that have been used for deep space missions. The Voyager missions, the missions to Pluto, all used something called RTGs, or radioisotope thermal generators. And these are systems that use the natural decay of plutonium to generate heat, and then again take that heat and convert it to electricity. The challenge is that there's a size limitation to how much power can be extracted from decaying plutonium. So these missions that have gone to deep space have been less than 1 kilowatt. So now we're looking at habitats on the moon that require hundreds of kilowatts, if not more. And if there are missions to Mars, they'll require thousands of kilowatts. So there's a limit to using the thermal the thermal generators, and the reason why we have to transition to something that's uranium-based or fission-based systems, as has been asked for in the Fission Surface Power program.
Well, that's fascinating. So are we currently using any kind of nuclear fission on the International Space Station or other low Earth orbit satellites?
So let me start with that one, Pete, and the answer is no, we're not. And so we have had some discussions with commercial companies that have an interest in perhaps replacing solar arrays on space stations with a fission-based power generation system. There are certain advantages associated with it, but there is the issue of anything that we put in low Earth orbit will re-enter the orbit and fall to Earth. And so having nuclear material that would be breaking up in the atmosphere and falling into the ocean, or heaven forbid in populated places, is not a good thing. And so there will be lots of discussions with governments before such a solution could be implemented.
Peter, I don't know if you wanted to share a thought on that, but please go ahead if you do.
I could just, so I agree with Harlan, definitely not on space station, given you've got crews on board. But I know there's some looks at it, but it's been mostly, I'd say, more for deep space exploration. There's been a lot of thought about, if you're going to look at trying to get humans to Mars, can I use nuclear propulsion as a way to do it in a much more expedient way, so I don't have 1 year to get there, 1 year to get back. Maybe there's a way to do it in a more accelerated fashion. But again, it's more architectural looks, more so than I would say implementing actual missions. I've heard of some SBIRs and some small study contracts to go do some of this work, but most of it's terrestrial-based investigations looking at concepts more so than flight demos.
I'll add that there was a mission that flew a reactor as a power source. It was called Snapshot. That mission launched in 1965. It used highly enriched uranium, and the reactor was called SNAP 10A. And so that was the last time that the U.S. flew a fission-based system for power generation in space.
I didn't even know that existed. That's fascinating. I know that, well, that was a period of time when nuclear was really very popular, right? Everyone was looking at this as an alternative power source. So that's absolutely fascinating. So did the SNAP actually go directly into space and not return to Earth, or was it, did it orbit Earth? What was its mission?
It was Earth orbiting. There were some sensors that were on board. It was also a plasma rocket demonstration platform. It didn't last very long. It did have an early failure on it. And as I understand from looking at Wikipedia, it'll continue to orbit the Earth for the next 4,000 years, but ultimately will re-enter. So we have some time to figure out how to handle that.
Oh, gosh. That is absolutely remarkable. Just incredible. Well, and looking, I was really fascinated, Harlan, by your presentation about how X Energy is developing an engine using nuclear power. And so what are the advantages of having a nuclear powered engine going into space? Of course, there's that it will propel itself for much longer, thinking of SNAP, right, for 4,000 years. But are there other advantages of using that kind of energy source?
Yep, sure. Let's start with looking at the architecture, where Pete started with Artemis. The architecture for a Mars mission using traditional chemical propulsion techniques and technology will end up with a system that will take about 9 months to get to the Mars orbit. Assume 2 months, 1 to 2 months, either orbiting Mars or doing a lander and then returning, and then another 9 months to return safely astronauts home. During that approximate 2-year mission, the amount of cosmic rays that the astronauts would be exposed to would be sufficiently high that very high likelihood of cancers, etc., due to cell damage that would occur from those exposures. So the first thing you think is, well, add additional shielding to the habitat for those astronauts. So you add shielding, you add weight to the system, you add the amount of propulsion and fuel and that's in cargo that's required. And so you end up not being able to, in NASA parlance, close the design. You end up not being able to deliver enough propellant and have a sufficient amount of shielding to have a successful mission. So you have to solve the mission solution a different way. And the way to do that is to improve the performance of the propulsion system. And so, chemical propulsion is an exothermic reaction. You're creating a hot gas and you're accelerating it through a nozzle. And so the idea that started in the 1950s was, why don't we use a reactor, a heat generation source, and we'll use that to superheat a gas, accelerate it through a nozzle, and we should be able to get much higher performance by doing so. And the analysis that has been done and some testing that was done in the 1970s showed that at least a factor of 2 increase in performance can be achieved by using nuclear thermal propulsion. So sounds like a great idea, right? Let's go do it. So the gas that they choose to use is hydrogen. You want a very small molecule to use as your propellant. Now, hydrogen has some interesting properties, and you store the hydrogen as a liquid at cryogenic temperatures. And then you allow it to boil off, and you pump it into the reactor chamber. And in the space of about a meter, that gas goes from 20 degrees centigrade to something on the order of 2,800 degrees centigrade. And by achieving that very high temperature, you achieve that very high propulsion performance that you need out of that system. But hydrogen is also a moderator. It affects reactivity, and it changes based upon what temperature it's at. So you end up with some very challenging controls problems that have to be worked through in designing such a system. And there have been a couple attempts since the 1950s to develop such a system. One was called the NERVA program. And NERVA started in the early 1960s, and I think it lasted until 1973 when it was canceled. But they went as far as doing a ground demonstration of this system out in the desert, and showed that this system would work. Unfortunately, the end result was that they partially melted the fuel and ended up ejecting melted uranium particles into the desert upon conducting that test. So the trick is to get to those very, very high temperatures for the propellant, and at the same time don't melt your uranium in the system. So there are a number of technical materials challenges that need to be addressed in developing such a system.
Well, absolutely fascinating. So I'm curious, Pete, for the Intuitive Machines missions, you have 3 missions that are coming up, and you were saying the mission duration is about 14 days. Is it possible that the energy will extend beyond that and the mission could go beyond that designated time frame?
Well, the current baseline design for our missions are to basically survive 1 lunar day. We do have batteries that will take us roughly, I'd say about 8 to 12 hours, maybe even longer into the lunar night. But it gets pretty cold pretty quick, so it's hard to keep things warm as you're going to the lunar night. You know, it's not unheard of if after 1 lunar day the solar panels are still there. The sun's going to come up, so you're going to get power generation off the solar panels. The question will be, really, will the batteries come back to life, and will the computer start up again? Right. That's what we'll find out from the first mission. And that's what we're hoping to see what happens. We are going to look at how it degrades as it goes into the first lunar night. The other thing we are looking at, though, is technologies where you can actually put a heat source or some way to keep that lander hot, at least parts of it, the critical parts, right, such that you could survive a lunar night and then come up and operate again for multiple days or even longer than multiple days. So there are technologies we're looking at to go do that we would employ maybe as early as our 4th lander, but that's kind of, you're going to have to do something physically probably to sustain or protect certain elements to keep the lander alive longer.
You know, it is incredible when you think about the extreme temperatures on the moon, and even more extreme when you get to Mars, right? Depending on whether you're in the sun or the shade, and having to design for that. Are there other ways that you could take advantage of the heat that's thrown off from the fission surface power source? You know, you were saying it's about 30% that's used to generate electricity, and the others is so 70%, right, is actually dispelled into the atmosphere. Are there thoughts about another way of capturing some of that energy or that heat that's being released?
I'll start by saying that there are several ideas that technologists have come forward with for using the residual heat that comes from the nuclear fission process. So, 30% efficient, 70% is waste. There's the opportunity for using that waste heat for perhaps taking regolith and getting the water that might be frozen in that regolith out. Perhaps using that heat for doing chemical processing to extract certain minerals or certain chemicals out of the lunar soil. So they have looked at other ways of using it. You can add additional power conversion systems, but while you might extract a little bit more efficiency out of your system, you are adding mass and weight to the system that needs to be delivered, as well as complexities to the overall system. So it really is a trade that says, how important is it for us to capture a little bit of that 70% of waste versus keeping the system straightforward, simple, and highly reliable.
So William, one thing I would add to that is, now I mentioned we were talking about ways to keep our landers alive. One of the architectures we've been looking at is using waste heat. So not that I need electricity to keep things alive, I just need heat to keep things alive. So if I can cage or control heat in a space where I have critical things, that may be one solution that we're looking at. So not quite tied to fission surface power, but it is tied into waste heat use, right?
Absolutely fascinating. So I was curious too with X-Energy, you had initially, the company started looking for solutions here on Earth. What are some of the lessons you hope to learn through the Lunar program and the partnership with Intuitive Machines that could have applications here on Earth?
That's a great question, and I'm going to give you two examples of why do we want to support exploration of the Moon and Mars, and when I meet with my company leadership, that is the first question that they ask is, we hope to produce hundreds of reactors for Earth-bound electricity generation and industrial process support. Why do we want to make one fission surface power reactor in the next 8 to 10 years? And the answer is that it enables us to push the envelope, developing a solution. And let's use the nuclear thermal propulsion as an example first. The terrestrial fuel that's used in light water reactors around the United States today, it resides inside metal canisters or cladding, and when that cladding reaches somewhere around 900 to 1,000 degrees Celsius, it melts, and you end up with a release of uranium, which is not a good day for a light water reactor. Using the ceramic coated or triso coated fuel that I referred to earlier enables us to increase the temperature of the nuclear fuel to up to 1,600 degrees Celsius in operation. And in fact, that fuel has been tested to 1,800 degrees Celsius and not exhibited any damage. So it's much safer fuel, and you have higher margins of safety in your terrestrial design. Now, if we're successful in developing a fuel design that can go to 2,800 degrees Celsius for a space application, for a nuclear thermal propulsion application, I can now take that solution and apply it to a terrestrial reactor, a commercial reactor, and I've just increased my safety case perhaps by a factor of 2. Or I've enabled my reactor to generate, we're a high temperature gas reactor. I can take my helium gas, which is my coolant for a terrestrial application, and maybe I can take it to 900 to 1,000 degrees Celsius, and now I can produce hydrogen, which is one of the goals of the nuclear industry, the Generation 4 nuclear industry, is to be able to support hydrogen production. So there are great applications for these cutting edge technologies that are developed for space that can be used here on Earth.
Well, I was also very intrigued by the idea of portable or modular surface fission that could be used here, especially in natural disasters, because we know that they're happening more and more often as we're even more impacted by them as a humanity with a growing population of the world. And people living in places where they're more prone to, natural disasters or other kinds of disasters. And we're so reliant on electricity. It's essential for human life now on Earth. I'm curious, Pete, about the missions for Intuitive Machines. Is there flexibility for the second and third missions? Because you hopefully will learn things from each mission, right, that will contribute. Are there some flexible goals in those missions in learning how surface efficient energy can actually better serve missions and better serve the future goals and aspirations of exploration on the moon?
So there are, the intent of our first mission when NASA first awarded it was really, it was really agnostic to landing location, and it was kind of a opportunity mission for science payloads. So they were really wanting to give us an opportunity to go land in probably what I would say is the smoothest, largest landing location you could find, right? So that you had a very high probability of success on your first mission and you could prove out a lot of your systems. And then we're about 6 months between missions. So once we fly the first one, we'll have the data from that one that we can apply into the second one, which is a little bit more of a threading the needle mission, because we have to, on that one, we're landing on the South Pole and we're coming in right at sunrise. And one of the biggest things you have to deal with on the moon is I don't have GPS. So I don't have navigational tools other than an optical camera that looks at the ground and says, hey, I know those craters look like what I expect here, so I know where I'm at. And then I roll over and pitch and I say, hey, that looks like something that's bigger than a bowling ball. I don't want to go land there. Here's a spot where I can go land. So I need to have some level of lighting to be able to go do that. And on the second mission, we also have a LiDAR, so we actually have ranging. So as we're coming in on that pass from darkness into sunlight, it's a little bit tighter mission. So we're going to learn a lot in that first mission that really prepares us for the second one. And then the third one is fortunately a little bit easier again, because it's back more towards mid-latitude, so we get a little bit better lighting condition. But we are coming in probably early in the day, so it's, but we will learn on each mission. Probably as much when I say landing, we're also going to learn how to operate and communicate. One thing we're learning, and I mentioned we have a lunar comm network. We've actually demonstrated our lunar comm network. We've been talking to the moon for several months now. Out of our control center here in Houston, we've been talking to NASA's Lunar Reconnaissance Orbiter in orbit. And in doing so, we've learned a lot. Comm is not always 100%, and it isn't always as easy as you think. And so, as we go out to the moon, we're going to learn how to operate and command it and communicate with it. And the amount of data we have to bring out on the first mission isn't that much, but there's a lot on the second and the third mission. So we're going to be learning how to operate and command it as well. So a lot of those opportunities in terms of thermal management, we're going to learn a lot about the thermal environment on the moon. We've done some pretty good analytics around it. We have a lot of good data. We have a partnership with Arizona State who operates LRO, so we've got a lot of insight into the environments. But we will definitely be able to inform a lot of the requirement sets and the environments that are going to be needed to survive for efficient surface power, especially when we go to the South Pole.
Oh, fascinating. Well, I'm curious how you gentlemen ended up in the roles you're in now. Kind of what is kind of your kind of trajectory in life? Did you know from the time you were young boys that you wanted to work in nuclear fission? I'm really curious about each of your journeys to where you are today.
I'd like to start. From 14 years old, I wanted to work in the space program, and I was successful, fortunate to enroll at Virginia Tech, and they had an aerospace and ocean engineering program. So from their perspective, studying moving through air is not that different from moving through water, other than some of your Reynolds coefficients might change a little bit. So I ended up taking classes in the design of offshore oil structures and ship hulls as well. But I wanted to work in the space industry, and I was fortunate in getting my first assignment with RCA Astroelectronics in Princeton, New Jersey, working on communication satellites. I did, after 10 years of doing engineering, and I moved to being a contractor with NASA Goddard Space Flight Center. I did go for an MBA, so both Pete and I have a Master's in Business Administration. I went to University of Maryland, and through that experience, in education, was able to move into positions of management. And it also enabled me ultimately to make the transition. I'm not a nuclear engineer, but I do know how to manage programs. I do know how to run an organization, and that was sufficient for my CEO to ask me to move to X Energy and run an engineering organization, except the nuclear engineering organization. So I do want to say every day I'm learning something new in regards to nuclear. I've been here for 7 years now, and there's always more to be learned in this discipline area.
Very interesting. Thank you, Pete.
So a little bit like Harlan, I was, I think I was a sophomore in high school, and one of my friends asked me pretty much, what do you want to be when you grow up? I said, well, I want to be an aerospace engineer and I want to work on space station. So 6 years later, I graduated from USC with a bachelor's in aerospace engineering on a Thursday, and Monday I started at McDonnell Douglas working on space station, believe it or not. And my first job out of college was the structural analysis work on the cupola, which I'm sure you've seen a lot of things up on station where people have been sitting taking pictures out of the cupola. Well, I did the structural analysis on that. And then after working about 6 years on space station, I went and got my master's in composite structures. So then I started doing a lot of work around composites. And I actually worked on DCXA, which was that vertical takeoff, vertical lander that McDonnell Douglas had way before SpaceX or Bezos was doing it. We were doing it back in the 80s or 90s, but it was a lot of fun, and did a lot of work around composites for several years. And then they actually converted me into sales, and that's how I ended up back into I got my MBA. I got pulled in to do tech sales support, writing proposals from a technical aspect, and my boss sent me back to get my MBA. So I got that and then moved into program management for an Army contract called Brigade Combat Modernization, or Future Combat Systems, and then got pulled back into sales and marketing for human spaceflight programs here in Houston for Boeing. But after 31 years with Boeing, I retired and thought I'd do something different. And I got picked up by Steve Ultimus, who was our CEO here at Intuitive Machines. And the first thing he did when I came in the doors, he said, go meet this guy, Harlan Bowers, and go write a response to this RFI on fission surface power. And that was the day I started getting a great education in nuclear systems. So Harlan taught me everything I know. So you can tell he's very smart in this area.
Well, those are fascinating backgrounds. And I always like to ask that question because we have many younger people who watch this series and they think about their careers and where they're going. And what it sounds like to me is you both have followed your passions and what your interests are. And you had definitely something you were aspired toward, but you also had flexibility to take different paths toward getting to where you are today. And I think that's truly inspiring. I'm curious about your visions for the future. What do you hope to see in, say, 5 years or 10 years time, and what the work you're doing will help enable?
Great question, William. I met with a group of congressional staffers about 6 months ago. They asked that same question of me, and my answer was that over the next 5 to 10 years, we will see traditional industries incorporating nuclear as their technique, as their method to reduce their carbon footprint and move to fossil fuel free processes. And so I have 3 examples. One is what we refer to as industrial process heat. And so this is factories and industries that use high temperature steam or high temperature gases for things like plastics manufacturing, petrochemical processes, fertilizer manufacture. And very recently, X Energy established an agreement with Dow Chemical to look at how to incorporate a nuclear power plant that generates high temperature process steam into their manufacture of those elements. A second example is the shipping industry. There's over 60,000 large cargo ships that are on the oceans every day, and almost all of them use some form of oil or diesel fuel for their propulsion systems. Several of them have made commitments to going net zero on fossil fuels by or carbon free by 2050. And one of the logical ways to do that is by incorporating small modular reactors as the power plants of those cargo ships in the near future. There are a number of regulatory challenges with doing that, but technologically it is feasible, and several of them are studying it today. And then the third is the application of the transportable reactors. And while not only is disaster relief in organizations like the Federal Emergency Management Agency looking at transportable reactors for things like disaster relief, but the Department of Defense has hundreds of bases around the world that are dependent upon diesel fuel for power generation at those bases. Some of them are very remote and difficult to deliver diesel fuel to, and they are all interested in going with carbon-free sources of power for those bases in the future.
So what do you think, Peter? What's your vision for the next 5 to 10 years?
So my vision, and we're focused primarily on what I would call the cislunar economy, or how things are going to grow in cislunar space, and that's the focus of our company right now. And we're starting to see, we're kind of at the beginning of this growth activity in cislunar space. If you had asked 2 years ago when I started Intuitive Machines, when we were in our first contract for Eclipse program, NASA basically funded about 90% of our mission. The second mission, NASA only contracted for about half of it, and we had to go find other payloads to fill out the mission to make it close. The third one, they're buying about 80%, but we're filling in the rest of the 20 as well. We're in the process of trying to manifest a commercial mission, a fully commercial mission, right? And if you'd asked me 2 years ago, I'd say that's impossible. But there's enough market or interest in areas and capabilities, whether it's in cislunar orbit or on the surface of the moon, where people are wanting to actually go do work. And there's funding in the industry, a lot of it private industry money, that's coming out with interest to go prove things or demonstrate things, and they see an economical back end to that. And as part of that type of an industry, we're also seeing the models shifting a little bit from what I would say is a very CapEx or how do I say, non-recurring intensive activity to more of an OpEx or more revenue based on services. And we're seeing a shift in the model in terms of what government can or wants to do, because they can buy things faster and they can get capabilities faster, leveraging commercial industry over what I would call traditional development contracts that are very dependent on government budgets and fiscal year budgets, right? And so what we're really seeing is a growth in the cislunar economy, where we're going to see more things landing on the moon. We're going to see humans returning to the moon. With humans returning to the moon, there's going to be a demand for more cargo to the moon. Power systems on the moon, the ability to move around the moon. One could argue there'll be a power grid on the moon, where you actually take a bunch of these fission surface powers and network them together to provide a larger base for operations. And we're going to start using the resources on the moon so we don't have to bring it all with us. Those are kind of the keys that I see that are going to unlock what is happening in and around the moon.
Just fascinating. Thank you both for sharing your visions for the future. There's so much opportunity, and I'm sure you have many more ideas. I appreciate your sharing just a few of those. And we are opening up so many possibilities. The commercial sector is burgeoning, quite honestly, and so many nations around the world are advancing exploration, and there's so many interesting collaborations that are currently underway. And so I really applaud the two of you for being on the cutting edge, the front edge of that innovation, and being so inspiring for all of our viewers. We're coming to the end of our time, and this has gone by so quickly, but I want to give you each an opportunity to share a final thought on this topic. So maybe start with you, Harlan.
We love the opportunity to juxtapose the aerospace industry with the nuclear industry. They've both been in existence for roughly the same period of time, starting in the 1940s to 50s. And moving forward to today, and the ability to take a lot of common approaches common systems and apply them in a different way creates a number of challenges, but the opportunities are tremendous. And as has been identified by NASA, there is no other way for man and woman to explore the moon, Mars, and other planets than having nuclear systems as a part of that solution. So we greatly look forward to nuclear electric propulsion, nuclear thermal propulsion, surface power systems, and other ideas that are certain to come up in the next several years.
Yeah, and I would add, when you look at what are the key items that you need to really sustain growth on the moon or on Mars, it's really power, water, air. I mean, if I have power, water, and air, I can probably sustain a presence. And so it's really critical when you think about it, getting that infrastructure in place to actually enable all that. And you can't wait till humans are arriving to do that. You kind of have to pre-position and get ready to do that. And so it's exciting when you look at a company like mine, which is what I'd call a new start aerospace company. And we do things, I'd say, a little differently. We're much more of a prototype shop. We do things quick and learn quick. And failure is an option because you learn faster, right? It's a different approach on how you attack problems. And when you take that approach, you marry it with some traditional aerospace partners like Maxar and Boeing, and then a green energy terrestrial house like X Energy, which we're kindred spirits because we're both co-founded and partly owned by Cam Gafarian. So when you put us together, it's a really good opportunity to provide different looks at how you solve this problem. So we're really excited to go do that, and it'll be a really quick year, I guarantee it.
Fantastic. Well, gentlemen, thank you so much for sharing your perspectives, views, backgrounds, and it was truly inspiring. And I'm really excited to see the results of some of the work and what we learned from your missions and the work that you're doing. But it's evident that you're going to change the world and change space through your efforts and innovations. I want to thank all of you for joining us today for this fascinating conversation. And if you are interested in exploration of the moon, Space Center Houston has recently opened a new exhibit on Artemis, where we're interpreting this incredible first mission on the return to the moon and the research and activities underway to prepare for humans to be on the moon, including the incredible work that these two companies are doing to help support creating a long-term presence on the moon to help prepare us ultimately to go on to Mars and beyond. Thank you again for joining us for today's program, and check out our other programs and activities at spacecenter.org and follow our blog as well.